Extreme event-aware ADA learning, a comprehensive explanation. The problem: why extreme events are hard to learn. Imagine trying to predict rare but catastrophic events like rogue waves, financial crashes, or extreme weather. These events are both infrequent and expensive to simulate. Traditional machine learning methods face two fundamental obstacles: data scarcity. Extreme events rarely appear in training data. Computational cost. High-fidelity simulations needed to capture extremes are prohibitively expensive. This creates a catch-22. Standard supervised learning models become accurate in normal regions but remain completely blind to rare extremes. As the authors demonstrate, even if you have 100 training samples, none might contain the extreme event you care about. The core insight: statistical regularization. The key innovation of ADA learning is elegantly simple: enforce statistical properties of extremes during training, even if no extreme examples exist in your data. Think of it like this: you're trying to paint a picture of a dragon, but you've only ever seen lizards. Standard approaches would just draw bigger lizards. ADA learning says, we know dragons have wings and breathe fire statistical prior, and uses that knowledge to guide the painting, even without seeing a real dragon. Mathematical formulation. The framework works as follows: input X, physical driver e.g. initial conditions, low-resolution data. State U, high-dimensional system state e.g. weather field. Observable Y equals GU, scalar quantity indicating extremes e.g. maximum precipitation. The learning objective combines two terms: text loss equals supervised loss plus lambda times Wasserstein distance learned distribution, reference distribution, where supervised loss ensures accuracy in data-rich regions. Wasserstein distance forces the model's output distribution to match a prescribed extreme event distribution nu. Lambda, balancing parameter. Theoretical foundation: why standard methods fail. The authors prove a hardness theorem showing that data-consistent estimators models that perform well where data exists necessarily fail in extreme regions when data is scarce. The theorem states, for a dataset smaller than a critical threshold, any estimator accurate in non-extreme regions will have a guaranteed gap from the true distribution, measured by the Wasserstein distance. This is intuitive: if you've never seen a 100-year flood, you can't predict its magnitude from normal flood data alone. The mathematical contribution is formalizing this limitation and showing why distributional constraints are necessary. The ADA learning solution. The framework addresses this limitation by 1. Incorporating prior knowledge. Nu, the reference distribution can come from asymptotic analysis e.g. wave theory. White noise approximations. Gibbs hypothesis. Unlabeled data sets. Hypothesized distributions e.g. generalized extreme value. 2. Optimal transport regularization. The Wasserstein 1 distance is chosen because it's mathematically optimal for controlling tail errors. In 1D, it has a simple quantile representation. It remains stable even when distributions have non-overlapping tails. 3. Tail emphasized training. Rather than matching the entire distribution, ADA learning focuses on the tail e.g. upper 2.5% quantile. This concentrates computational effort where it matters most. Practical implementation, making it work. The authors develop sophisticated training strategies, ERM pre-training. The model first learns the input-output relationship from available data, then the distributional constraint is applied. This prevents the regularization from destroying useful learned patterns. Tail set selection. Instead of evaluating the Wasserstein distance on all samples, the algorithm periodically evaluates all auxiliary inputs. Identifies which inputs correspond to tail quantiles. Only backpropagates through those selected samples. This reduces memory cost by 40x from 9044 to 226 samples in their precipitation experiment. Gradient balancing. The regularization strength lambda is adaptively set so that the Wasserstein gradient has comparable magnitude to the supervised gradient, preventing one term from dominating. Real-world applications. The paper demonstrates ADA learning on 3 challenging problems. 1. Precipitation downscaling. Given 0.5 years of high-resolution HR data and 25 years of low-resolution LR data, ADA learning generates statistically consistent extreme precipitation fields. Matches the true HR tail distribution. Outperforms standard MSE models that completely miss extremes. 2. Correcting deep generative models. ADA learning serves as a statistical corrector for flow matching models trained on limited data. It elevates the tail distribution of generated samples to match ground truth, outperforming HR models trained on the same limited data. 3. Hypothesized extremes. Even when the true distribution isn't known, ADA learning can enforce any hypothesized extreme distribution, e.g. heavier tail GEVD. This allows exploring what-if scenarios for risk assessment. Key insights and limitations. What ADA learning does well. Generates statistically plausible extreme events. Preserves accuracy in data-rich regions. Provides theoretical guarantees via optimal transport. Works with multiple types of prior knowledge. What it cannot do. Uniquely identify extreme events. Different ADA models can produce different extreme locations while matching the same observable distribution. Guarantee physical correctness. The model may generate extremes in physically impossible locations. Identify mechanisms. Matching observable statistics doesn't reveal why extremes occur. The trade-off. There's a fundamental tension. Emphasizing extreme statistics slightly degrades pointwise accuracy in non-extreme regions. In precipitation downscaling, RMSE increased by 8.13% while structural similarity remained nearly identical. Broader implications. ADA learning represents a paradigm shift in data-driven extreme event modeling. From data to knowledge, it shifts focus from requiring extreme examples to leveraging statistical knowledge. Bridging supervised and unsupervised learning, it can use unlabeled data to inform extreme statistics. Risk-relevant AI, critical for safety-critical applications where missing extremes is unacceptable. Climate adaptation, enables exploring plausible extreme scenarios under climate change. Conclusion. Extreme event-aware learning provides a principled framework for learning about rare events without seeing them. By combining supervised learning with statistically informed distributional constraints, it bridges the gap between data availability and the need to predict catastrophic events. While it doesn't guarantee perfect prediction of individual extreme events, it ensures that a model's output statistics remain physically plausible, a crucial property for any system where rare events carry the most significant consequences.